All right, dude, we are live again for the second time today. What's up, guys? This is Dem Keys, and um, I'm restarting the stream. Well, I already restarted the stream. Um, actually, I don't think I needed to say that. It's why did I even mention? Anyways, I started the stream earlier, and then I stopped it because there was some connection issues, which still seem to be present, unfortunately. I don't know what's going on. Um, Wait, what is going on? Hold on. I think things to reduce the load on my network so that I can continue to stream. For some reason, there seems to be a load on the network. It shouldn't be happening, but it's happening. Give me a second. We are off to a rocky start of the stream, but it's okay. Give me a second while I just make sure everything is running. Okay, everything seems to be running, but we are still dropping frames and like the stream is buffering and stuff. So I don't know if I should. Let me try a couple other things to reduce the load. Oh God, chill out, chill out. Okay, that's done. There is something else that I can turn off as well. That's hopefully gonna reduce the load. Okay, okay. Uh, we seem to be stable now, I think. Kind of stable. Kind of stable. Give me a second while I just do a bunch of things to try and reduce the load. Wait, I don't know. Is this an issue on? No, this is an issue on my end. I was wondering if it's an issue on my end or on Twitch's end, but I have a couple other streams running, as in other people's streams for, audio stimulation, visual stimulation, stuff like that. And even those streams started to buffer. The thing is, they're all Twitch. Like all the streams are running on Twitch, so I still don't know if it's a Twitch issue or my issue. And even like OBS is showing like red and yellow, like the signal thing, it's showing red and yellow. Um, I don't know if that indicates an issue with connecting to Twitch or if it's indicating an issue with my connection. So, what should we do? What should we do? Right, so we are 5 minutes into the stream. I could restart the stream, but like if the signal is still just because the signal is still going into red and yellow, I'm not sure if restarting the stream is really going to do anything. Because I've dropped like 30% of the frames so far in the stream. Restarting the stream is really going to help. Either way, yeah, let's just get into it. Whatever. If it works, it works. What's up, guys? This is Dem Keys, and today we are going to be picking back up from where we left off yesterday. Though not exactly, because where we left off yesterday, I was on this page. Hold on, this page, which is I I had to stop this. I think somewhere here. I don't remember exactly where. It was somewhere here. I had to stop it if I remember right, because it had become quite late already. Uh, so I had to end the stream, but then I carried on reading stuff here. I finished reading all of this, and I got up to this point, and then I read the implementation, and then instead of trying to implement this, I tried to apply this implementation to the previous example that was given. The previous example was this thing. It was, okay, I've changed a lot of the code here, so give me a second. Okay, so the basic idea here, an input X, and we have weights, and we have a bias, and we have a target variable, or rather, well, an expected, the expected value, and then X and W, and then adding the bias to that result. So we do a basic linear transformation there, and that gives us Z, which is our predicted output. So Y is our expected output, and Z is our predicted output. So we then use Z and Y to calculate the loss, and based on the loss, we then calculate the gradients, and we are then able to use the gradients to update the weights. So when I looked at this, when I looked at this code, and this is something I'm still trying to understand, because from what I've noticed here, and this could just be because I, don't have a full understanding of it yet. Give me a second. Let me just check the frames. How are we doing? Frames seems to be going. Oh, I'll take it. Okay, cool. Right. So something that I noticed with this, so over here, the optimization method we are using is stochastic gradient descent. But what I noticed about this, I still, I could be completely wrong. I haven't looked into the, what am I trying to say? I haven't looked into the calculation of stochastic gradient descent, but when I tried to understand how gradients get applied to the weights, or how the gradient is used to update the weights, the only thing that I was noticing there was that we were scaling the gradient value down by a learning rate. So we 0.001 or 0.0001 or something like that, a very small amount. And that becomes our multiplier. And then we multiply the gradient with that amount, and then current weights. And that's basically the weights. And also from the bias, we subtract it from the bias as well. And that becomes our words. What was I trying to say? That becomes our new weights and bias, and then the process just repeats. So this is how we are updating the weights. From my understanding, this is what stochastic gradient descent is doing, though I don't know yet. I need to read up on stochastic gradient descent. In fact, let me just open up the so we can see if that is the case. I probably shouldn't have done that, because it's going to put a load on the network and we're going to start losing frames again. Okay. Seems like we are good. Kinda, kinda good. Okay, while this is loading, I guess we can transition back. Yeah, I shouldn't be opening up web pages and stuff, at least during today's stream. And I'm glad that I don't have any musical smoothness properties. Um, it can be regarded as a stochastic approximation of gradient descent optimization since it replaces the actual gradient by an estimate thereof, especially in higher dimension, wait, especially in higher dimensional optimization problems. This reduces the very high computation. Stochastic gradient descent can be traced back to so-and-so's algorithm of the 1950s. Today's stochastic gradient descent has become an important optimization in machine learning. Okay. Um, in stochastic gradient descent, the true gradient of QW is approximated by a gradient at a single sample. As the algorithm sweeps through the training set, it performs the above update for each training sample. W equals W minus, where the parameter W that minimizes QW is to be estimated. Okay, each summoned function Q is typically associated with the ith observation. Okay, dude, no, I'm not getting this. Yeah, I'm not I'm not getting this. So I think there is something slightly more complex going on in stochastic gradient descent. Something a little more complex than just made me think of subtracting the value. Yeah, I can't remember what made me think of that. Though what I could do, okay, let me explain what I tried to do. So in one of the previous chapters, actually in the immediate previous chapter, the very last chapter that we were reading, um, which was talking about, which was teaching us about autograd, which was teaching us to get the grades after calculating the loss and doing back propagation. So in that chapter, it there was this example presented for a very simple one neuron calculation where you have an input with n number of features and you pass that input to the neuron. The neuron has it has weights. The number of weights will depend on the number of features in the input. So you have to make them match, and it has a bias as well. And then you also have an expected output, which is y, and whatever result you get from the linear transformation, that becomes z. And so after you get that result, you pass that into after you get that result, you pass that into this function, binary cross entropy with logits, and you use that to calculate the loss. After getting the loss, you call loss dot backward to calculate the gradients for the weights and the bias. It stops at that point. Like, we calculated the gradient and we got the gradient. In the next chapter, we use the gradient uh, to update the weights and bias, right? Only in the next chapter they were doing it with an actual a proper neural network implementation, not this single neuron implementation. What I did is I tried to apply that implementation to our single neuron example. And that was kind of interesting because I also plotted it here. This is basically showing the loss over these many iterations. So I ran, I didn't do it. I did like one sample per epoch. And so I had to do multiple epochs. I had to do a lot of iterations, which was fine. And I tried experimenting with different learning rates, like smaller learning rates versus bigger learning rates. And what you're seeing here is basically, this is called plateauing, where the change in the value, it kind of stabilizes. And once it starts to stabilize, this is our loss basically. So the loss started here, and we kept on minimizing the loss by updating the gradients, and gra- wow, voice crack. Gradually, we got to this point where it kind of started to stabilize. I think this point, or would it be this point? I can't tell because it seems pretty flat here as well as here. But somewhere at this point, it starts to stabilize, and then there isn't too much change from that point on. So it was kind of interesting. I was playing around with this logic yesterday. I set up my own training logic here. So far, it's only the training logic. We haven't done the testing part yet. It's mainly the training. And what I want to try is, so each time I'm passing, okay, this idea just occurred to me. Each time I'm passing, wait. So we have fixed weights, right? Okay, so each time I'm passing in the same, at, how do I say this? At each run of this cell, I generate one random input value. What I want to try doing is, what if I try generating a bunch of different input values? So instead of doing it here, instead of doing the generation here, let me also not print this out. Instead of doing the generation there, let's generate the input here. So at each iteration, it's going to be a different value. Let's see how that changes this thing. Let's see if it helps the network. Uh, okay, so the thing is, so far I'm just playing with numbers. I'm not doing anything meaningful with the network. I think what the network's score, for lack of a better term, um, what the score is supposed to be, I think that depends on what you're trying to do with the network. Um, are you trying to classify something, or are you trying to predict something, or are you trying to do something else? I also feel like at this point, maybe I should step away from this thing that I'm doing here and start using the actual neural network, the proper neural network structure. Well, I mean, to be fair, I could set up the thing without a neural network structure as well. I could set it up as a linear thing. Yeah, I could set up one linear layer. I could do that. Yeah, yeah, yeah. I didn't think about that. I could set up one linear layer. Something else I didn't take into account is this is like the raw value. We are not doing any transformation on it. We're also not applying any nonlinear activation functions. I don't know if that somehow makes a difference. Something interesting to notice here. Okay, so uh, understand that so far I'm just playing around with the idea of training and the logic of training. I haven't yet gotten to the point where my training is yielding something useful. But what I want to try and do is um, I want to try and apply neural networks to a specific problem. Because here's my understanding. Okay, we have a neural network. It's initialized with, like, let's say it has n number of layers, and those layers have n number of neurons, and each of those neurons are initialized with so and so weights and so values, random values for the weights, random values for the biases, right? We want, let's say the purpose of this neural network is to map a specific input to a specific output, or at least predict something close to that. We want the neural network to learn this mapping. And the way that it learns this mapping is through this repeated iterative process, throughout which the weights get updated. And eventually, we are able to get the weights and biases to a point where passing in the input is gonna give us either the exact output or something close to the output that we are expecting. So we want the neural network to learn this mapping. This is a problem that I want to try and apply to neural networks, or rather, this is a problem that I want to try and apply neural networks to, and see how well that works out. Because I've tried this exact same example with, and I guess in a way that kind of falls under classification, doesn't it? I think so. I think so because the fashion MNIST example is a pretty good example of exactly this. What we are trying to do is we are trying to make it so we pass in a certain input, which is the image pixels, and the network predicts the correct classification. The network classifies this image with the correct label. So it's essentially the same thing as what I'm trying to do, mapping a certain input to a certain output. And it's kind of interesting to think about because what we are doing here is we are making this network learn this mapping by constantly updating the weights based on the mistakes that the network makes. The mistakes that the network makes are they're represented by the gradients, which are calculated by the loss. I find this interesting because we are able to, I'm not able to put it into words because I'm able to visualize it, but like if I had to explain it in words, basically we are trying to create a linear system, or a system that does linear transformation, that does calculations in the form of linear transformations, but the two variables that would be used in those linear transformations, we are updating those variables values, and the values that we assign to those variables kind of dictates what the final result is going to be, and thereby it dictates how good or how bad the network is going to perform. And we are able to update these two variables, which are the weights and bias, in order to make sure that the calculation is accurate, or the prediction, or well, classification is accurate. I don't know if I explained that very well, but like I'm able to picture this in my head. I'm just not able to explain it very well. There's something really interesting about this whole concept where we take a neural network and we train it, we update its weights, basically we train it so that we are able to pass in some input and get the expected output. Yeah, I'm 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 able to picture that. I'm not sure if my explanation is really is really expressing how I don't know. I find that really interesting. And this is just like we are still in only feed forward neural networks. We haven't even touched convolutional neural networks and recurrent neural networks. Convolutional neural networks is definitely going to be the next thing that I'm going to go into. I need to watch the MIT lecture on it. I've actually watched it before as well, but I need to rewatch it just to get like a better idea of what's going on there, and then I want to try and construct my own CNN using PyTorch. But okay, for now, this is what I have. I don't. The thing here is I feel like I was trying to focus on minimizing the loss without really thinking about what the network is supposed to be doing. This is one, I guess, perceptron is the accurate term. So something I've noticed here is the term perceptron. It used to have a different meaning, and now it has a different meaning. Because I kind of see places where the entire network gets called a perceptron, and in some places one layer gets called a perceptron, and in some places one neuron gets called a perceptron. And I've tried asking Google Gemini about this, and it gave me a similar answer to what I was thinking. It's that the term tends to be used interchangeably, because in the past it meant something else, and then as the tech kind of evolved over time, the meaning kind of changed. Hold on. What was this? What was I asking? There was a question. I was plateau. Yeah, I was trying to understand what the term plateau means. Okay, so let's try asking Llama. What was I gonna ask? Oh yeah. Okay, I'm learning deep learning. I'm confused about whether a perceptron is a layer or a neuron in the layer. Because okay, I think another reason why I had this confusion was, first of all, I was seeing it being used interchangeably, right? Another thing that made it confusing was you also have something called a multi-layer perceptron, and when you say multi-layer perceptron, that's kind of a feed-forward neural network, right? Multiple layers. So then the entire network is being called a perceptron. Okay, let's read what. Oh, good. Okay, MLPs are covered here as well. Okay, in the context of wait, actually, in 15 seconds there's going to be an ad playing, so I'm going to start the ad right now, and I'll see you guys in 30 seconds, and then we'll do this whole reading thing. All right, welcome back. So let's continue. In the context of deep learning and neural networks, the term perceptron and neuron are often used, but they have distinct meanings and historical contexts. Here's a classification to help you understand the difference. Perceptron is a historical concept. The perceptron was introduced by Frank Rosenblatt. I don't know if I'm butchering that name, but It was introduced by this person in 1957. Dude, it's crazy to think, and I've read the history of neural networks, not completely, but like when I was doing research on neural networks, I did get introduced to a bit of the history, and it's crazy to think that these things were if not if not implemented, at the very least theorized, like way back when. Because like, dude, I've seen videos, and I think they were black and white videos, or they were in the very early days of when color videos had become a thing. Like, um, before we had actual, like, color videos, it was mostly black and white, right? And then gradually the tech kind of allowed the tech advanced to a point where they were then able to move to having color in videos. And this was like very early on. So like my point is, I don't remember what the video was. Otherwise I would have, actually I don't think I would have pulled it up because of copyright BS. But there is a video of some theoretical physicist, I think. Yeah, there was a person who was theorizing that at some point in the future, we are going to have these machines that we are able to control, that we are able to tell what to do. And at some point later, we're going to have these machines that are um, as our own personal machines in our homes. They were talking about computers, in case that's not clear. The person was talking about computers. I don't think they called it a computer because at the time, I don't think computers were a thing. They had these machines, but I don't know if they were calling it a personal computer. I think they were calling it something else. But yeah, it's kind of interesting. My point is, it's kind of interesting seeing how these things were kind of like theorized back in the day, even though there wasn't a practical implementation of it at the time. They were theorized back then, and then years later or decades later, the thing was actually implemented because years or decades later, technology actually allowed us to do it. Okay, anyways, let's carry on with this. I don't know. It's really interesting for me just thinking about how these things were theorized back then, even though those people didn't really know, or no, actually, they knew. That's why they were theorizing it. They knew based on their calculations and their knowledge, they were able to make these theories that theoretically this would be possible. But they were able to make these theories and theorize these things despite not having a practical implementation of it. Okay, let's carry on with this. So the perceptron was introduced by Frank in 1957 as a simple supervised learning algorithm for binary classification. Dude, I haven't heard this term in a while. I was hearing about binary classification, or I was reading about binary classification back when I had started learning about machine learning. And because there were so many topics for me to look into in machine learning, I kind of just, like, I saw the term. I didn't really look too deep into it. Maybe we could look up binary classification real quick. Give me a second. Okay, so it seems like my network has stabilized and I don't think we are doing that bad, but I don't know. Let's not push it. Uh, okay, binary classification. Okay, the page is also loading much quicker, which is great. By the way, is the middleware app still running? The reward system is connected. Chat system is connected. Was there any other system? I don't think so. I think that's it. Okay. By the way, I do have ideas for stuff that I want to add to the middleware app, and I still need to make the app open source, dude. I haven't. I've been busy with so many other things that I haven't had the time to sit down and make a public repo and upload this code there. I'll get to it eventually. Okay. Wait, did I transition back? Yes. So, binary classification is a task of classifying the elements of a set into one of two groups. Oh, that's why it's binary. Each called each called class. Okay, so classification. Okay, so you can classify it into one of two classes. Okay. Typical binary classification problems include medical testing to determine if a patient has certain disease or not. Okay, so it's a yes no thing. Quality control in industry, deciding whether a specification has been met. Again, I think that's also technically yes or no. Is it yes or no or more than that? Because it says um, classifying the elements of a set into one of two groups, and it's binary as well. So like that's two, right? Binary. Oh shit, I hit the mic. I have no idea what that just sounded like, but like holy shit. Are we good with like is did the mic disconnect? No, the mic is fine. Okay. We are good. Where was I? Yeah, in information retrieval, deciding whether a page should be in the result of a search or not. Oh, does binary search also come under this? Like if is that what this is? Okay, then in administration, deciding whether someone should be issued with a driving license or not, and in cognition, deciding whether an object is food or not food. Okay, when measuring the accuracy of a binary classifier, the simplest way is to count the errors. But in the real world, often one of the two classes is more important. So that wait, what? But in the real world, often one of the two classes is more important so that the number of both of the I'm trying to make sense out of this sentence while reading it and it's just not working. Let's hold on. Wait, let's try that again. But in the real world, often one of the two classes is more important so that the number of both of the different types of errors is of interest. I'm okay, whatever. For example, in medical testing, detecting a disease when it's not present, as in a false positive, is considered differently from not detecting a disease when it is present, which is also which is a false negative. Wait, hold on. That's interesting. Wait, for example, in medical testing, detecting a disease when it's not present is considered differently from not detecting a disease when it is present. Okay, so they have this diagram here showing, or well, they have this chart, I guess, graph showing false negative, true negative, non-positive negative. What is NP? Okay, then there's true positive and false positive, and then there's FPR, PPV, TP. Okay, this is dude. Okay, this is kind of interesting. Wait, scikit-learn. I say wait a lot and hold up a lot. Anyways, scikit-learn binary classification. Does scikit-learn have binary classification? Because scikit-learn does have classifiers, it does have classification methods, classification algorithms. I don't know if specifically binary classification is in it or not. Um, I should look into the classification side of scikit-learn. I've looked into the clustering side, more specifically only k-means clustering. I need to look at the other algorithms as well. Dude, there's so much for me to explore, but I don't have time. There's only so many things that I can give my time to. Okay, let's look at the classification section. I just realized I'm not doing it on this screen. I'm doing it on a different thing. Okay, uh, sklearn classification. So there's supervised learning, and under that there's classification. Okay. So we transition back, open this up, and in here, where was it? Uh, oh, there it is. Oh, dude, support vector machines. That's also another topic that it came up a couple of times in my early machine learning days, but I never really looked into it too much. Mostly because like linear regression, it tends to be like the okay, I don't know if it's accurate to say that, but I've seen it in a lot of different situations. So based on that, I'm saying it. Linear regression tends to be like the hello world of machine learning. So like when you're learning machine learning, then there's a decent chance that you're going to be introduced to linear regression. At least that's how it was like back in the day. Back in the day being a good like 5 years back. Not even 5 years back. I think it was 6, 7 years back, but around that time. Um, Linear regression was the first thing that I was introduced to, and there were a bunch of these other things because like I looked into machine learning, and then I looked into the different categories of machine learning. You have supervised learning, unsupervised learning, and then reinforcement learning, and somewhere in between there's also semi-supervised learning. And I was trying to explore all of these things to get as much knowledge as I could. But like these are very, very vast fields. So like each of them by themselves, they are really vast fields. So it's you can't really explore every single thing. You have to kind of pick and choose things that you're going to focus on and like study those things. Um, so yeah, okay. Support vector machines. Support vector machines are a set of supervised learning methods used for classification, regression, and outliers detection. Okay. You know what? I'm going to keep this open for now. Um, I just realized we kind of branched out way too much and we stepped really far away from what we were originally doing, which is this. We'll get back to this. Hold on. Let me finish reading up on this perceptron versus neuron thing. Okay, so the perceptron was introduced as a simple supervised learning algorithm for binary classification. It is essentially a single layer neural network with one output neuron. Okay. The perceptron algorithm is designed to learn a linear decision boundary and can only handle linearly separable data. Okay. Perceptron versus neuron. Neuron. In modern neural networks, a neuron or artificial neuron is a basic computational unit that receives one or more inputs, performs a computation on those inputs, and produces an output. Neurons are the building blocks of neural networks and are typically organized into layers. Perceptron. The term perceptron specifically refers to the original algorithm and its single layer neural network. However, in modern usage, each neuron in a multi-layer perceptron or any other neural network can be thought of as a perceptron because they both perform similar computations, which is weighted sum followed by the activation function. Okay? Multi-layer perceptron. An MLP is a type of feed-forward neural network that consists of multiple layers of perceptrons, neurons. Each layer in a multi-layer perceptron is fully connected to the next layer, meaning every every neuron in one layer connects to every neuron in the next layer. This structure allows MLPs to handle non-linearly separable data. So what I'm getting here is, okay, because like when you call a feed-forward neural network a multi-layer perceptron, and then you also say that each neuron can also be thought of as a perceptron, this is basically where my confusion was coming in, because we are calling the entire network a perceptron, albeit a multi-layer perceptron. We are calling it a perceptron, and then we are calling each neuron of that multi-layer perceptron also a perceptron. Key points. Each perceptron, no, each neuron is a perceptron. In the context of modern neural networks, each neuron can be considered a perceptron because it performs some basic operation, taking weighted inputs, summing them, and applying an activation function. Layer composition. An MLP is composed of multiple layers, each containing several neurons, perceptrons. These layers work together to process complex data. So an MLP is a multi-layer perceptron, meaning the neural network itself is a perceptron, but at the same time, each neuron of that perceptron is also a perceptron. Okay, let's see what it says here. The terminology around multi-layer perceptrons and perceptrons can be somewhat confusing, but here's a clarification. Multi-layer perceptron. An MLP is a type of neural network, feed-forward neural network that consists of multiple layers, an input layer, one or more hidden layers, and an output layer. Each layer is fully connected, meaning every neuron in one, yeah, okay, fine. Every neuron in one layer is connected to every neuron in the next layer, fine. Perceptron. The original perceptron introduced by so-and-so is a single so-and-so, whatever. Cool. Neurons in an MLP. Each neuron within an MLP, including those in the hidden layer and output layers, perform a similar computation to the original perceptron. Here's what that means. Okay, I know what that means. Comparison to perceptron. You know what? Okay, I'll get into this later on. For now, let's do this thing. Um, what I wanted to do is let the weights and biases be okay. So let's create a sequence. Actually, not even a sequence. Let's create a layer. Okay, layer nn.linear, and we're gonna have. Wait, did I not run the thing? Oh yeah, I think I need to run the thing. So let's run this. And after that, we should be fine here. So what are we looking for? We're looking for 3 input features and 1 output feature. So it gives us 1 value. And that's going to be our random. Okay, cool. Wait, is that done running? Yes, great. Okay, so let's print this out. Let's see what it gives us. 3 in features, 3 out features, and there is a bias. Let's print out the weights. Random weights. And it requires grad. True. Okay. There's also a bias. 1 bias. Great. The number of biases, I believe it depends on the number of neurons, which depends on the number of out features, which in this case is 1. Great. So we have our linear layer. Now let's create an input. Um, let's say, let's give it a fixed value. Now, wait, it's expecting 3 input features, right? The weight matrix is going to be transposed. I need to keep that in mind. If the weight matrix is going to be transposed, that means it's going to be 3 rows, 1 column. It's going to be 3 rows, 1 column. Okay, wait. So in order for the matrix multiplication to work, hold on. M by P, P by Q. M by P, P by Q. An M by P matrix can only be multiplied by a P by Q matrix. So if P is this, we need 3 columns. Okay. So our input is supposed to have 3 columns. So let's say 0 0.2, 0 0.1, and 0 0.3. All right. What else do we need? Are we just calculating our output? I guess so. Yeah. Okay. So let's just do that. Now, what is Z? So Z is going to perform. Actually, how am I doing? Oh, yeah, I need the binary, not the binary. I need the cross entropy loss thing. I don't remember what the name was. Wait, did I make a mistake here? 3 columns, right? 1 row, 3 columns. Uh, hold on. What am I missing here? Oh, am I supposed to wrap this into a row? No. Wait, what is the shape of... Okay, that became 3-dimensional, so that's not gonna work. All right. Yeah, it's one. Oh, wait. I'm supposed to do 3 rows. Am I supposed to do 3 rows? No. Okay, if X is an M by P matrix, it can only be multiplied by the weight if the weight is a P by Q matrix. So if the weight gets transposed. If the weight is a 1 by 3 matrix, oh, it's supposed to be a 3 by 1 matrix. Okay. So here's what I need. Wait, isn't that what I did? I created a 3 by... What am I missing here? I'm missing something because if I just did this, that shouldn't work. It works. Okay, great. Why does it work? This is a 1 by 3 matrix. Um, Hold on. Let's print this, print out both the shapes. So the weight matrix is a 1 by, oh dude, I think I was doing it the wrong. Yeah, well, I mean, clearly I was doing it the wrong way. Yeah, I was doing it the wrong way. The way that I was defining it, I think what I was defining was 3 rows with 1 column. Yeah, I think that's, well, I mean, that's why it was saying 3 by 1 shape. I was supposed to do 1 by 3, right? And if the weight matrix gets transposed, then the weight matrix becomes 3 by 1. Um, so this, okay, all right. All right, fine. So now that we have that cleared up, so this is our value. Okay, so we need to create an expected output, which is also going to be a tensor. Um, let's say 0.25. Okay, then we have z, which is our output. Then we calculate the loss. Wait, this returns a tensor, doesn't it? Okay, so no, not binary. What was it? Cross entropy. Cross entropy loss. Right, isn't that what's being done here? Dude, I could very easily just follow this example, but like my own way of understanding is trying to apply it to my own example. Like that's my way of understanding it. Okay, so we have the loss function. Oh, maybe I should write it like that. Loss fn, and then I can have a separate thing for loss. So that can be loss fn, and we pass in z. Where does the loss function get called? It should be in the training loop, right? Loss equals so and so. Oh yeah, we are to pass in the prediction and the expected value. So z and then y. And then we print out loss. The loss is -0. That's interesting. Okay, here's what I should do. I should print out everything. Um I should print out the weights. So let's say W equals LO1 dot weight dot, actually that's the entire thing. Okay. And then let's print out the bias as well. Let's also print out X, because why not? Let's also print out y because why not? And then let's also print out z because, why not? Okay, let's format this so it mentions loss, and I think we are good. Great. Okay, so our weights are, these are our weights. This is our bias. This is the input, and this is our result. Okay, what if we change, yeah, what if we change that? The loss, dude, is the loss being calculated properly? I'm not sure if it's being calculated properly. So we have the loss function, model.train, okay, model.eval. Wait, where's train and eval? Hold on, train and eval are part of, where's the class? That's it. Why does this say model.eval? Does this by default have, does the model by default have, wait, let's create a thing here. Um, okay. Oh, it has a train function. Set the module in training mode. This has any effect only on certain modules. See the documentation of particular modules for details of their behaviors in training/evaluation mode. Okay, all right, all right. So we're gonna have to look into that bit as well. Now, about the loss function. So this is our training loop, and all we are doing here is defining this, and then we are passing the loss function in. But it's not doing anything. It's returning, what is it returning? It's returning negative 0.0. Right, what if I try different inputs? So let's say x equals torch.rand_n, um, 1 row, 3 columns. Nope. I think I'm doing something wrong with calculating the loss. Yeah, I think I'm doing something wrong with calculating the loss. Hold up. Does this require the entire neural network structure, like the proper neural network structure for it to work? Okay, input so and so. No, it doesn't seem like it requires it, right? Target equals torch.empty, so and so. Loss equals this, loss dot backward. If the loss is 0, what's the gradient going to be? Let's do loss dot backward. Um, and then we should be able to print the gradient for the weights. So that would be weight dot grad, yeah, and then bias as well. Yep, it's not doing anything. What am I missing here? Right, so let's try doing the calculation, okay? The expected output is 0.25 and the predicted output is negative 0.7338. Let's write out these weights and let's write out the input as well. The weight was, it would be, um, it's a 1 by 3 matrix multiplied by 3 by 1 matrix. So it's gonna result in a 1 by 1 matrix, right? So I would have to, this is a markdown cell. Okay, so I would have to do, wait, so if I take the transpose of the weight matrix, that would make it so I need to, hold up. Right, okay, so that would be 0.1027 multiplied by 0. Actually, let's do it like this. 0.0159 plus negative 1.6061 multiplied by 0.5679 plus negative 0.97 multiplied by 0.1243. And that gives us this. Oh, bias. I forgot the bias. What is the bias? Right, the bias is 0.2972. All right, so that is accurate. That is negative 0.7338. Now, I feel like I need to think about, like, what are we trying to do here? We are trying to make the network map one value to another, at least for the time being, or well, map a set of inputs to one value, and we are trying to get the network to um, learn this relation, learn this mapping, right? Why is the loss 0 though? I'm also curious about whether negative zero means something here. What is negative zero point 0.0? Wait, I need to see if, okay, PyTorch, uh, loss, negative zero. You know what? Hold on. So these would be considered logits, right? Well, no, the result would be considered a logit, right? Is there a thing like with logits here? So there's BCE with logits loss. Let's try that. Okay, now we actually have a loss. That's interesting. So I need to see what was happening in cross entropy loss that was causing this. Because cross entropy loss is still giving 0 0.0. What exactly is going on in this that is doing that? When we call this as a function, the loss input target. Okay. So here, wait, am I using this wrong? Let's take a look at the example. So in cross entropy loss, what is the prediction? Where's pred being defined here? Oh, pred is here. Pred is the result, which is this, right? Yeah, z. That's exactly, yeah, okay. Yeah, dude, I'm not getting why this is happening. I guess one of the reasons is because I don't actually understand how cross entropy loss works. That could be why I'm not really able to make sense out of this. Okay, let's try this. PyTorch cross entropy loss returns zero. Returns negative zero. Classification problem. Okay, all right. Cross entropy loss is negative. Cross entropy losses gradient is zeroed out by my something. Okay. Yes, it's perfectly fine to use a loss that can become negative. Your reasoning about this is correct. To add a few words of explanation, a smaller loss, algebraically less positive or algebraically more negative, means better predictions. Oh, you know what I could do? After running, I could make this bit dynamic because now I know it's, a linear, like the linear transformation is being done. So what I could do is I could multiply this with LO1 dot weight dot transpose and then add the bias, right? This should give us, that's not right. Hold on. Oh, it's not doing a matrix multiplication. How do I wait? This did a element wise thing, I believe. How do I? Okay. Would it be matmul? I think yes, matmul. All right. What is z? Something is wrong here. So weight dot transpose is multiplied with x. Hold up. Let's try running this again. Those are our weights. That's our. Hold on. Is the does the order matter here? Matrix product of the two tensors. I don't think the order would matter, would it? Because like we could be multiplying. Oh wait, no, the order would probably matter. Yes, the order would matter because if we are multiplying a 1 by 3 matrix with a 3 by 1 matrix, the result is a 1 by 1 matrix. But if we are multiplying a 3 by 1 matrix with a 1 by 3 matrix, the result is a 3 by 3 matrix. So the order would definitely matter. What am I missing here? Because my Z is coming out different. Oh, okay, that's what I'm missing. B is something else somewhere in the code. I'm supposed to be doing bias. That's what I was missing. Okay, now back to trying to understand why cross entropy loss is not returning anything useful, but binary cross entropy loss with or BCE with logits loss is returning something useful. Cross entropy loss, mean squared error loss. We need to go to the loss functions. Also, give me a second. I need to take a short break. I'll be back in like, I don't know, couple minutes. I'm gonna mute the mic and there's no music, so it's just gonna be quiet. But I'll be back in like 2 or 3 minutes. Okay, I'm back. So let's get back to, you know what? I think the connection is stable enough now that I can try and play the thing on my stream. What am I saying? I can try to well, I mean I'm doing it already, so there's no point in saying it, but I've started saying it, so I'm going to finish saying it. I'd paused, so I have my stream manager open in on another machine on another screen, and that's just to make sure that my stream is showing what I want it to show, and I'm not accidentally on like a different screen, like on BRB screen, or you know, uh, I can also figure out if the stream is frozen or something like that. So that's why I have my stream playing on another machine, more specifically in my stream manager. And because of the earlier internet problem that I was having, I had to pause the video player. So yeah, I was just unpausing it, and we seem to be fine. It doesn't seem to be negatively impacting anything. I think I can also carry on playing somebody else's stream on another machine. Uh, I don't know if I should push my luck. There was actually another thing that I needed the internet for as well. So I'm just going to enable one of those things just so I'm able to see it. Give me a second. All right. So, yeah, back to this. Now, why is it that, oh, hold on. Um, wait, shit. I missed the ad timer. So there's going to be an ad starting in, I don't know, 10, 15 seconds. So what is this? L1 loss creates a criterion that measures the mean absolute error between each element of input X and target Y. Input X and target Y. Input X and target Y. Okay, what does cross entropy loss say? This criterion computes the cross entropy loss between input logits and target. Okay, let's ask Llama what exactly are logits, just so I have a proper understanding of what exactly it is. Because so far the only thing I know about it is that whatever is returned by the neural network is what we are calling logits. Oh, also there's an ad playing right now, but in the next 5 seconds it's going to be over, so whatever. Okay, welcome back from the ads. All right, so logits are a fundamental concept in machine learning and deep learning, particularly in the context of classification tasks. Here's a detailed explanation of what logits are and how they are used. Definition: raw outputs. Logits are the raw unnormalized scores or outputs generated by the last layer of a neural network before any activation function is applied. Oh, hold on. I wanna try something. um, let's say AC01 relu, because it mentioned that these are raw outputs. There's no nonlinear activation function applied to it. So then Z equals AC01 Z. And now if we try running this, wait, we need cross entropy. Oh no, okay. Still, still nothing. Yeah, I'm not entirely sure what I'm missing here. Though, to be fair, I'm trying to get a value out of, like, at this point, we are still at that point where I'm just playing with numbers. This network is not meant to be doing anything meaningful. And something meaningful could even be something as simple as mapping one value to another. But right now, I'm not really trying to do any of that. I'm just trying to get values from the functions. Um, but okay, so we ran this. Okay, the input is that, and oh, okay, yeah. The input is this, and the output is this. But the expected output for this input is this. Right? So there's clearly a loss there, but it's not reporting any loss. Oh, you know what? Cross entropy loss always returns 0. PyTorch, PyTorch cross entropy loss always returns 0. Okay. You are in a multi-class classification scenario, which means you can consider your problem a C binary class classification done in parallel, where C is the total number of class. Okay. Having output T, the logit tensor containing the values outputted by your model's last linear layer, and target, the ground truth tensor containing the true classes state. Okay, states for each instance in the batch. You can apply BCE with logit's loss since it works with multidimensional tensors. This is okay. This is fine, but you didn't answer. You didn't. I guess what I'm trying to understand is why cross entropy loss is giving 0. Okay, somebody has this exact problem that I'm having, that it only returns negative zero point 0.0. I've not looked at your code, so I'm only responding to your question of why so and so returns negative 0. Okay. Note that the target can be interpreted differently depending on its shape relative to the input. If target.shape is equal to input.shape, then target is interpreted as having class probabilities. I think this is what's happening in your case. Cross entropy of so and so is 0 because cross entropy function is taking target to mean the probability of class 0 should be 1. Then, since input is interpreted as containing logits, it's easy to see why the output is 0. You are telling the loss function that you want to do unary classification, and any value for input will result in a 0 cost for the loss function. Probably what you want to do instead is to hand the loss function class labels. Okay, so I think what it comes down to is that I'm using it the wrong way. That might be it. I think that might be it. Yeah, I think I need to properly understand what each of these loss functions are doing instead of just plugging values into them. I think that might be it. Um, all right. That being said, what does oh wait, what was the other one? BCE something? BCE with logits loss. This loss contains a sigmoid layer and the BCE loss in one class. Okay. This creates a criterion that measures the binary cross entropy between the target and the input probabilities. The unreduced loss can be described as so and so. Man, I need to. This was one of the reasons why I was trying to avoid. Dude, I need to get a high level understanding of what's going on. I mean, as long as it doesn't go down into calculus, which it seems to be doing here, as long as it doesn't go down into calculus, I think I can stick. I can try to understand the calculation. Okay, let's try reading this. Let's see. Actually, hold on. This says that this loss combines a sigmoid layer and the BCE loss in one single class. This version is more numerically stable than using a plain sigmoid followed by a BCE loss as by combining the operations into one layer, we take advantage of the log sum exponent trick for numerical stability. Okay, let's take a look at this. Where n is the batch size. Hold on. The unreduced loss can be described as, oh, okay, so this is the loss function, right? And then this is the entire calculation. Um, what is this supposed to? This seems like a transpose of something, a transpose of a set. What is L supposed to be here? Or what is the big L supposed to be? Ln, where n is the batch size. If reduction is not none, the default is mean. Then the loss function is equal to the mean of L if reduction is mean. The mean of L, this is used for measuring the error of a reconstruction in, for example, an autoencoder. Note that the target's Y should be numbers between 0 and 1. Oh, that's only going to happen if I apply relu first and then okay. You know what? Okay, let's test that out. Let's see. So, hold on. X, Y. What is L supposed to be here? Ln equals this whole thing. Okay, dude. How am I supposed to read this? Is it negative weight multiplied by whatever is in here? I'm not good with reading the how do I say it? Because like math algorithms are written in a specific way. I'm used to reading the programmer math algorithms, but with this stuff, I have to. Oh, you know what? Let's ask Llama. I'm trying to understand. Wait, wasn't I reading this? And then at some point, I had kind of gotten distracted. Okay, role in classification, transformation into probabilities. You transform it using a softmax function or a sigmoid function. But softmax is different, isn't it? Is softmax also an activation function? I know sigmoid is an activation function, but is softmax also an activation function? Um, hold on. What is this? This is nonlinear activation functions, weighted sum nonlinearity. What is the next section? Nonlinear activations. Okay. No, this is nonlinear activations as well, but weighted sum nonlinearity, and then okay. So both of these are nonlinear. Softmax is also a nonlinear activation function. Okay, back to where I was. Yeah, interpretation, confidence scores. Logits can be interpreted as confidence scores or the model's belief in the presence of each class. Higher logit values indicate higher confidence in the correspondence. Have I been understanding the have I been understanding the output wrong? Because I was imagining that the output would be what the input maps to, right? So like we get the neural network to map a given output to a given out did I say output? Map a given input to a given output, and then that given output we compare it to what the expected output was supposed to be. Wait, what is that doing exactly then? Yeah, how does that make sense? Like we are trying to get the network to map. Oh, no, we are trying to get the network to map a given input to an expected output. And then we calculate the actual output and then compare that with the expected output to calculate our loss and then calculate the gradients and then update the weights. Okay, that's what we're trying to do. Because okay, I was trying to understand how confidence scores come into this because could it be that I'm understanding this wrong? Well, okay, no, hold on. Cross entropy loss could be doing that, right? Because no, this is saying logits. At this point, we haven't really passed the thing through anything except for one linear layer and one activation function. Okay, it mentions loss functions here. During training, the model learns to adjust its parameters to minimize the loss between the predicted logits and the actual labels. Okay, so the prediction is what's called logits. Okay, this process involves optimizing a chosen loss function, such as cross entropy loss, which quantifies the discrepancy between the predicted probabilities uh, obtaining obtained after applying softmax or sigmoid and the true labels. Wait, it quantifies the discrepancy between the predicted probabilities. Oh, so yeah, the predicted output and the true labels, the true output. Okay. Key points. Unbound nature. Logits are unbounded, meaning they can take any real value, whereas probabilities are bounded between 0 and 1. Linear relationships. Before applying nonlinear transformations, logits represent the linear relationships with the model, which is which is which is fundamental in understanding the initial process of inputs. What? The initial processing of inputs by the model. All right, so logits are the raw output of the network, of the network's last layer. If it's the raw output of the network's last layer, oh, okay, after the last layer, we are not applying any nonlinear activation function, right? We are applying the activation functions before. Yeah, because I'm thinking back to the very first neural network that we had made, which was a simple like three-layer network, right? So you have your input that then goes through the first layer, then it passes through a ReLU, then it passes through a second layer, then another ReLU, and then the last layer. But after that, there's no ReLU. Okay, let's right. So I kind of get it. I kind of um we can we can explore that later on. All right, help me understand what cross entropy loss is and how it works. For context, I'm using PyTorch. So, like I mentioned before, so far I'm just playing with numbers, right? I'm not doing anything useful with the network. Um, at some point, I need to start doing that. I need to start trying to use the network to do something useful, do something meaningful, even if it's something as simple as mapping input X to to expected output Y. Because even if I'm able to do something simple like that, that would also be great because that would also teach me something about neural networks. Because I want to try and apply neural networks to many different types of problems. Because I feel like it's going to teach me about how to apply, obviously, how to apply neural networks to different types of problems, but it'll also teach me more about neural networks and their workings, or more specifically, the workings of the various building blocks of neural networks. Also, quick side note, I was thinking about this yesterday, how any given neural network may not necessarily always be as simple as, you know, just a feed forward neural network, or just a convolutional neural network, or just a recurrent neural network. Because libraries like PyTorch, they allow us to build fairly complex networks, right? They give us the building blocks, and then how we put those building blocks together is completely up to us, right? It allows us to create a very customized neural network based on whatever our requirements are, and that those requirements may not necessarily always be just, one type of neural network. And that's where I feel like visualization can get a little bit complicated, because I was using NNSVG for trying to visualize feed forward neural networks and convolutional neural networks, and it's great. Like that tool is amazing as long as your neural network is like a fixed size, or not a fixed size, a fixed type. But when you try to combine different types of layers in there, that's where things can get a bit complicated. That's where you might need a different tool instead. Um, so I think in addition to NNSVG, I'm gonna have to look at other stuff as well, because NNSVG is going to be super useful for initially visualizing a bunch of things. But once I start going into more complex architectures that involve a bunch of different types of um, layers, and a bunch of different types of activation functions, and with CNNs you also have pooling functions that come in. There's a bunch of like different things, right? Recurrent neural networks might have their own extra set of things, extra set of function types. So once you have like a bunch of these different things getting mixed together, I think at that point visualization gets a bit complicated. So I'm gonna have to use there. Fortunately, there are a bunch of different tools available to do this, but they're not all as straightforward as NNSVG. Because with NNSVG, you could just specify the parameters and it draws the entire thing for you, right? But with other tools and libraries and stuff, you're gonna have to like define the entire thing yourself. Um, though the plus side of that is that you would be able to visualize what you are trying to visualize. So you're gonna get an accurate visual representation, hopefully, of your neural network. Okay, let's carry on reading. So, what were we? Yeah, we were reading about cross entropy loss. Cross entropy loss is a widely used loss function in machine learning, particularly for classification tasks. Here's a detailed explanation of what I'm just going to say CE. CE loss. Nah, nah, that's dumb. Cross entropy, cross entropy loss is, and how it works, especially in the context of PyTorch. What is Okay. What is cross entropy loss? Cross entropy loss measures the difference between two probability distributions, the true distribution of the labels and the predicted distribution by the model. Okay. It is derived from the principles of maximum likelihood estimation and used to evaluate how well the model's predictions match the actual labels. Okay. All right. So my assumption here is that the actual predictions are also numbers, and the model's predictions are also numbers, and that's how we are comparing them, because they keep calling them labels here. I'm assuming that the labels are associated with some kind of number, or they are represented as a number in some way. All right, types of cross entropy loss. Binary cross entropy loss. This is used for binary classification tasks where there are only two possible outcomes. Example 0 and 1. Is that why I'm getting 0? No, I'm not doing binary. I'm doing just cross entropy. Okay. The formula for binary cross entropy loss is so and so, where y is the true label and y hat is the predicted probability of the positive class. Multi-class cross entropy loss. This is used for multi-class classification tasks where there are more than two possible outcomes. The formula for multi-class cross entropy loss is so and so, where yi is the true label for class I and y hat is the predicted probability for class I. How cross entropy loss works. Calculation. Cross entropy loss calculates the difference between the true labels and the predicted probabilities. For each sample, the loss reflects how well the model's prediction matches the true label. Okay. A lower loss value indicates a more accurate prediction, while a higher loss value suggests a larger discrepancy between the predicted and true labels. Give me a second. I'm gonna take a small break. Um, just like 2 minutes. Okay. All right. So, back to reading this. Give me a second because my stream manager's video player crashed. For a second, I thought there might be some issue with the stream, but fortunately, we seem to be fine. We are not losing a whole bunch of frames, so I think we're good. All right. Okay. So, back to reading. Softmax activation. In multi-class classification, the raw output scores, logits, from the last layer of the neural network are typically passed through a softmax activation function to convert them into probabilities. Okay, so all softmax does is um, take a set of values and normalize them down to a point where if you summed up, well, normalizes and also does some calculation on them to convert them into a set where if you summed up all of those values, it would sum up to one. That being said, what does it do? What does it do if it's just one value? Like imagine I did, okay, so let's say nn dot softmax, okay, and instead of AC1, let's pass it through AC2. Isn't that just going to give one? What did I call this? Oh, I called it AC1. Yeah, isn't this just going to give one because there's just one value? Yeah, there it is. Z is now one. Okay, so softmax is it has its own uses for specific things. I need to figure out in what situations I would be using softmax because I can definitely see it being useful in certain other cases, but like my specific case, it's not useful. Though I guess, well, yeah, okay. I was about to say, though I guess it would depend on what the specific case is, and yeah, okay, whatever. When using PyTorch's cross entropy loss, you do not need to apply the softmax function explicitly because it is internally handled by the loss function. Wait, it internally applies softmax? Okay, all right. Here's an example of how to use cross entropy loss. Okay, all right. So this is a two-layer neural network. We have one layer and then ReLU and then the last layer. And our result is outputs and targets. Okay, how is targets calculated? Targets is from the data loader and then inputs is from here. We pass, oh, it's using I think it's trying to use data from, it's using, it's, how do I say this? It's, well, okay, I was about to say it's using data from Fashion MNIST or one of the other data sets, but I think the assumption with this example is that you're using some kind of data loader, which is going to give you both inputs and targets. Okay, so, right, let's assume we have our inputs and let's assume outputs is logits, right? And then we pass that into cross entropy loss and compare it to targets. Targets is our expected value, I'm assuming, right? And then we get loss. So this is using it in the same way that I was trying to use it. Though, to be fair, um, I think what this is trying to do, what this network is trying to do is classify something, not necessarily predict something. It's trying to classify a given set of inputs into a specific label. Okay, so up until this point, I haven't used optimizer. Like I haven't used it in this way. I've only um, I've been manually optimizing the weights without using something like SGD, I just noticed this thing where you are able to, okay, so when you define an object of stochastic gradient descent, you pass in model dot parameters. This encapsulates all of the parameters of the model, which is super convenient, especially when you have multiple layers, multiple neurons per layer, and so each neuron's weight matrix could be any number of rows and columns. It's super useful that you're just able to pass model dot parameters, and it has like a link to that. And then of course your learning rate. And this is even more convenient. You do optimizer dot zero grad. I'm guessing this just sets the gradients for all of the parameters to zero, because um, apparently the gradients add up if you don't set it to zero. I haven't tested that myself, but like I read it somewhere, and so it's recommended that you zero out the gradients for the weights and biases before you calculate backward, or before you call backward to do backprop. So it's convenient that you're able to call optimizer.zero, and that zeroes out all the gradients for the weights and biases, and then you call loss.backward and then optimizer.step, and optimizer.step is what updates the weights. Optimizer.step is where the weights and biases get updated based on the gradients calculated with loss.backward. Now, another interesting thing that I've noticed with this whole thing is the use of that computational graph, because all of the stuff that you're doing, like it's being recorded into a computational graph, and that is why AutoGrad is able to generate the gradients when you call loss.backward. So I need to get a good understanding of how that computational graph is working. Fortunately, there's a good bit of documentation, a good chunk of documentation available on the computational graph and how things work. So I'm gonna be reading that as well to get an understanding of it. But yeah, it's convenient. It's convenient that you're able to collapse a bunch of lines of code down to just these statements. The optimization step is as simple as this. You zero the thing out, and or rather the entire training process is as simple as you zero out the gradients, calculate new outputs, calculate new loss based on the outputs, calculate the gradient, and then call optimizer.step. So you then update the weights and biases based on the gradients, and then you just keep repeating that process. And you basically end up with something similar to this. Okay, where was I? Okay. So, yeah, the example is great. Cool. Key features and key features and implications. Probabilistic interpretation. Cross entropy loss encourages the model to output predicted probabilities that are close to the true class probabilities. This is because the loss function penalizes the model for predicting probabilities that are far from the true labels. Oh yeah, okay. Based on this loss function, we'll then calculate the. I was wondering how the loss function is penalizing the model, but yeah, it's because based on the loss function, we calculate the gradients, and then those gradients are used to update the weights, so it is directly affecting the model. Okay, gradient descent optimization. The mathematical properties of cross entropy loss make it well suited for optimization algorithms like gradient descent. It provides a stronger signal for the model to update its weights when the predicted probabilities diverge significantly from the true labels, leading to faster convergence. Okay. Handling class imbalance. Cross entropy loss can be combined with techniques like class weights or focal loss to handle class imbalance problems. This helps the model focus more on the minority class and improves performance on imbalanced datasets. I didn't fully understand this, but I think I might see an example of this uh, in like future in future neural network examples. Okay, now if I'm being honest, okay, I got a bunch of information about cross entropy loss, but something that I haven't connected the dots for in my head yet is how I'm meant to be using this. Yeah, because I feel like my brain is still sticking to that one thing that I was trying to do where um I was trying to make I was trying to make the neural network learn a linear relation between a specific input and a specific output. I'm trying to get the neural network to learn that. Though if I'm trying to do that, I shouldn't be using the nonlinear activation okay, I'm not doing that. Okay, cool. What if I tried a different loss function? Oh, you know what? I could ask. I'm trying to train a neural network. Actually, let me be more clear. FCNN to learn a linear mapping between input X and expected output Y. Which layers and which layers, activation functions, and loss functions should I be using? Also, in yesterday's stream, I kept trying to remember a specific neural network architecture, a specific neural network type. I wasn't able to remember the name of it. And I was saying that I'd been seeing that name pop up a couple of times with other people who do use neural networks. The name is Control Net. Um, at some point later, I'm going to be looking into that as well. Okay, to train a fully connected neural network, to learn a linear mapping between input X and expected output Y, you can follow these guidelines for choosing the appropriate layers, activation functions, and loss functions. Okay, layers. For a linear mapping, you do not need complex nonlinear transformations. Here's what you should consider. Fully connected layers. Use one or more fully connected dense layers. Since the mapping is linear, you can often get away with a single fully connected layer or a minimal number of layers. A single fully connected layer with no hidden layers can be sufficient for a simple linear transformation. If the relationship is slightly more complex but still linear, you might add one or two hidden layers with a small number of neurons. Activation functions. For a linear mapping, you do not need, that's what I was thinking. You do not need nonlinear activation functions. Um, Here are your options. No activation function or identity activation. Identity activation. That's interesting. Okay. Since the goal is to learn a linear transformation, you can use you can use no linear activation function or an identity activation function, which simply passes the input through unchanged. Okay. So then at that point, you're just having an activation function for the sake of having an activation function. In PyTorch, you can achieve this by not specifying an activation function after the fully connected layer, or by using nn.identity if you need to explicitly define it. Okay. Loss function. The choice of loss function depends on the nature of your output. Why? Here are common choices. Mean squared error if y is continuous and you are predicting real valued outputs, MSE is a suitable choice. Okay, there's MSE loss. Then there's mean absolute error. Another option for continuous outputs, mean absolute error can be more robust to outliers compared to mean squared error. Okay, example architecture is this, and it's just one linear layer. Okay, okay. No activation, nothing. Okay, cool. MSE loss. Let's try. Okay, you know what? Let's try. I might need to redo this whole thing just so I can fit it into a training loop. Okay, so we are gonna do that. We are gonna create, let's say, an input. Actually, we need a linear layer, right? The linear layer has to be outside. Yes, so LO1 equals linear layer, one row, three inputs, or well, one sample, three features. Actually, it's not even one sample. Well, no, it is one sample, but here one and three doesn't mean that. Here it means something different. Okay, anyways, that's L1. Then we have X, which is our input. So that's torch tensor. Let's say 0 0.1, 0 0.2, and 0 0.3. So we want to map this to Y, which is supposed to be 0.25. So we want to map this input to that output. Okay, what else? What else? Yes, z equals LO1 x. Great. And then loss function equals nn.mse, and loss equals loss function. Wait. Oh, MSE loss. Loss equals loss function. First is the predicted output, and then is the expected output. So we get our loss. Actually, hold on. This whole thing is supposed to be happening elsewhere, right? So here, right, this is where our epochs come in, our epochs and our learning rate. So we're going to do about 2000 epochs, and our learning rate, man, my voice is starting to give out. Okay, so our learning rate is, let's say 0.001. Or let's make it smaller so that, it gets distributed better in the 2000 iterations. Oh, we also want loss values. I'm going to be updating this. Okay, so for I in range, I think. Yeah, range epochs. We calculate the loss. Oh, we should also zero. Yeah, hold on. Okay, there's two ways. There's two ways that I can go about this. One, I could try applying. Um, okay, we can try both. So let's do weight.grad.0. Or maybe I should apply that at the end. No, we can apply that at the beginning as well. That's fine. The thing is 0 to begin with, so it should be fine. Okay. Then we calculate this. Actually, loss function is just once, so we don't need to keep defining it. All right. So we calculate z, we calculate the loss, and then we calculate the gradient of the loss, or the gradients of the loss. And then with torch no grad, this is actually what made me realize that I need to look into the computational graph, because if I don't do this, and if I try to update the weights and biases, yeah, if I try to update the weights and biases just like that, it's going to throw an error, like without no grad. So I need to do it within a no grad context. So lo1.weight, what is it? Minus equals what? Yeah, lo1.weight.grad multiplied by learning rate. Okay, and then we do the same with the bias. And we should be, at some point I need to add this as well, right? Okay, so we want, what are we trying to plot here? The gradient or the loss? We can start with we can start with the gradient. So loss values dot append loss dot item, I think it's loss dot item, or it's loss dot data dot item. I'm not sure. Yeah, I think it's loss dot data dot item. Hold on. A equals tch tensor 0 1, and then we want to get a dot is item here. Yes. So this is for individual items. This only works with tensors with one element. Right. Okay. So we want to record that. And then at the end of all of this, once it's done, we want to call plot from matplotlib and plot the values. So let's run this. Okay, we have an error. None type object has no, oh, okay. So I'm guessing the gradient type hasn't been set yet. Uh, if is not equal to a thing in Python? Yeah, I think it is. I think just checking one of them should be fine. Okay, there's still an error. There's an issue with the shapes. X's shape is the issue. What's the problem with X's shape? Okay, it's saying these two shapes cannot be multiplied, but wait, this is supposed to be, so it becomes a 3 by 1 matrix, right? Okay, why is that an issue then? Like this is what it's supposed to be. X is supposed to be a 1 by 3 matrix because W is going to be a 3 by 1 matrix because it's going to get transposed. Why is this an issue? What was I doing previously? One row, three columns. Isn't that what I'm doing here? Wait a minute. Hold on. X dot shape. No, let's print X dot shape. The size is one row and three columns. Why is there an issue, dude? Oh, yeah, that's my mistake. It's supposed to be three input features and one output feature. Now we should be fine. Okay. So now we give it a bit, let it finish its computation, and there it is. There is our, um, I don't know if it's accurate to call this gradient descent because this isn't exactly gradient descent, but like based on the gradient, we are updating the, we are updating the, based on the gradient and the learning rate, we are updating the weights and bias. Um, okay, let's do this. Okay, that's much better. So it's learning much quicker. All right, so once this has been plotted, I think one last time, oh shit, I missed the add timer. Okay, once this has been plotted, I think one last time that we can run a prediction. Actually, once it has been plotted, now I think one last time we can run a prediction and see what the loss is. Yes, the loss did go down to 0. All right. So let's do this, and it is supposed to be between our predicted loss and our predicted output and our expected output, and then we print out loss. Okay, there is an ad playing right now, so I'm going to take a little hydration break, and I'll see you guys in, well, now like 15 seconds, but yeah, let me take a hydration break. All right, welcome back. Um, so now we're gonna test this out. Let's add a thing here. Uh, Testing phase, let's call it. Let's format this Z equals this, and loss equals this. Oh wow, the loss is so minuscule that it gets displayed like this. Holy shit, that's crazy. Okay, yes, this is okay, that's why it's like this, because there is still a bit of a loss there, but it is super close. It mapped it to instead of 0.25, it mapped it to 0.2427, which is interesting. I need to look into this as well because it's close, but it's not a one-to-one mapping. So I feel like there's something that I can study there. There's something that I can study um, to understand what's going on. That being said, I'm super happy with this because now we actually have a thing. Now we actually have we've accomplished what I was trying to accomplish. First of all, we have our very first neural network that we have trained, and we have trained the neural network to map a given input to an expected output. And of course, we trained the neural network to to get to that point. So we constantly updated it. We constantly updated its weights and biases to be able to get to the point where it is able to map this specific input to that specific output. How small is this? By the way, this okay through through PyTorch, I finally got to that point where I'm going to be able to remember this scientific notation of E hyphen 05 and shit like that. So just to give you an idea, um, this is the same as writing this. Like this is scientific notation for writing this. The E over here is basically 10 to the power of. And what that means is we are saying 1 multiplied by 10 to the power of negative 3, because the hyphen is supposed to be a negative. Oh, wow. Encoders, hello, hello. Thank you for the raid. Welcome to the stream. Welcome, raiders. Um, wow, I haven't gotten raided in a long time. Holy shit. That's, yo, thank you for the raid. Hello. Oh, yeah. Uh, thank you for the raid. Hello, encoders and no encoders and raiders. Yes. I'm Dem Keys. I I like learning things, and I like coding, and usually that's what I do on stream. Give me a second. Let me give you a shout out. What is my shout out command? This. Yes. But yeah, thank you for the raid. Welcome to the stream. How are you doing? Is the NN working? Yes, it is. So okay, I'm a complete beginner in neural networks, and so far I've been learning about feed forward neural networks, and finally we got to the point where I was able to train the neural network to map a given input to a given output. I finally wrapped my head around that. Initially, we were having some trouble with one of the loss functions, but I think the reason for that was because I didn't understand what exactly that loss function was doing, and so I was just using it wrong. Hello, Tej. I'm gonna call you Tej. Hello, welcome to the stream. What are you curious about? But yes, encoders. To answer your question, I did get this specific neural network working, and I'm happy about that. That's my very first. This is my very first neural network that I made. It's mainly for mapping one input to one output. Now I want to explore more things like classification and predicting new types of output based on certain inputs. But there's a lot for me to explore here. A lot for me to learn, I guess. Okay, so where where was I? By the way, yes. Since you just rated in, if you need to step away to do post stream things, post stream care, feel free to do that. And anyone else who has come with the raid, um, feel free to just relax. Or if you need to step away as well, that's perfectly fine as well. So what are we doing now? You know what? I could now that I've done this mapping thing, I could go with I could go along with this example. Oh, yes. Okay. There's so I wanna try using the optimizer now instead of so in 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 this in this version of the training loop, I used my own sort of um let's say algorithm for correcting the weights and biases. Now I want to try and use stochastic gradient descent instead. We're still going to plot the loss and see what that looks like. Okay, so let's say optimizer is nn dot, I forgot what it was. What does the code say? Torch. Okay. Torch dot optim dot, I think there's another. Okay. And in here, we want to pass in, does this have parameter? Yes, it does. Okay. And then LR would be this. All right. So once we, oh, something froze. Okay. Yeah. So once we, um, once we are in the training loop, we do, I guess, optimizer dot zero grad. So we zero out the grade. I wonder if putting it into the optimizer handles that one situation where I had to check if the gradient was none or not. I think it might, because in this example it doesn't seem to be checking. So I think internally it might be handling that situation where if gradient is none, then it's just not going to do anything. Okay. What else did I need to do? After backward, we don't need to do this. We directly call step. All right. Loss.backward, optim.step, and that should be it. All right. So the only thing that's random here is the weights and bias. Yeah. The only thing that's random here is the weights and, actually I just remembered I was about to do this, Right. So let's calculate how small that other, this is Python, right? Yeah. Let's calculate how small that loss was. So it is this multiplied by 10 to the power of that. Okay, it's still too small. So it's yeah, that's oh, I could try putting this into llama. Hold on. Um Give me this number. No, wait. Give me this number without scientific notation. So that's how small our loss was. It was 0.00005 something. That's crazy. Here, what was I doing? Yes, I was gonna test out using an optimizer instead of using my manual weight update method. Okay, something is an issue here. It has no attribute SGD. Okay, let's try this. Oh, sorry. I hit the mic. Okay, are we done? Yes, we are done. Okay, so this is interesting. Here it actually went a little above. I feel like there's something for me to explore here to understand what makes it go below or above the value. Here it's perfect. Well, okay, so I guess it also depends on the way it's in. Oh, this one is off. Well, not off by too much. Either way, yeah, it seems like the dude. Let me try plotting the grade. Actually, I can't plot the gradients for the weights because we have three features, right? We have three input features, so the weight matrix is going to be, yeah, no, that's not going to be a single value. So plotting the, yeah, yeah. The weight matrix is a 1 by 3 matrix. So the gradient is also going to be a 1 by 3 matrix. So I can't really plot that. I could plot for one. Oh, you know what? Let's try just one value. Just one in feature. So we can map um let's map this. So let's map 0.1 to 0.25. Right. And now hold on, give me a second. Let me refresh my thing. My what? My stream manager. Yeah. Let me refresh that because the chat was kind of bugging out. Okay. So what was I gonna do? I forgot what. Oh yeah. Okay. So X has one feature. The linear layer is expecting one feature and it gives out one feature. So even the gradient is then going to be one, right? So let's try though. the gradient is going to give us, it's going to tell us by how much the value has to be changed. Well, no. Yeah, actually, no. Gradient gives us the magnitude, doesn't it? And a direction as well. Okay, let's try that. What was I going to do? Yeah, loss. Okay. Loss dot append. Um, this should be LO1 dot gradient. Maybe I should do, maybe I should do it here. Or let's have a different statement altogether. Okay. LO1 dot weights. Yeah. Weight dot gradient. This is a tensor, so we'll call item. Okay. So let's try plotting this. That's interesting. Oh yeah, it starts with negative. So that's what the gradient looks like. Interesting. Though I guess it would depend on what the weights are initialized as, right? Because the weights can be initialized as positive or negative, and depending on what they're initialized as, we can test that out. Wait, let's print out the initial weights. Um, initial W equals LO1 dot weight. We can also do the initial bias. So, okay, all right. Though, okay, so what we are trying to update here is, oh, you know what I should do? I should try and figure out how changing the bias would affect things here. Yeah, I should try figuring out how changing the bias would affect things here. Though I don't know if I would find much of a difference if we are just doing like a linear mapping. Yeah. Would I? I don't know because it's one value. I mean, at that point, the bias, not entirely sure if it is even. Though, okay, what we are trying to do with the neural network, with this one neuron network, is we are trying to get it to figure out what the optimal values are that, when multiplied by the input, would give us the expected output. And that is how we are making it learn how to linearly map this input to that output. Right? So I guess in that case, if I removed the bias, we could the network could still learn, right? So if I zeroed out the bias, though I don't think manually setting it is the best idea because it messes with autograd. At least I think it does. I remember reading about that. Like you're not supposed to manually set the weights and the biases. There's a way to go about doing that. Oh, okay. You know what else we could try? We could try creating multiple mappings. How do we do that? Okay, this right. So we have um one sample, I guess we can say. Give me a second. Let me drink something. Okay, yeah. So let's say one we have one mapping right now. We have one. How am I supposed to say this? We map one input to, let's say, one label. That's the best way that I can. That's the best thing that I can think of right now. One label in Y, right? We want to map one input to one label. Let's say I want to introduce more labels in here. Let's try to keep the label. Wait, how? That's interesting. Wait, no, that's a yeah, that's an interesting problem. How am I mapping multiple different values to multiple different labels? What would be a good approach there? We could have multiple samples, but then the input is only going to be one input. We still need to map it to one label out of multiple labels. Get the how do we get the oh, we need multiple training samples and then one test sample. Yeah, yeah, okay, this is where the training data comes in. Because okay, here we were trying to map one so far we were trying to map one value to one other value, and that works. That's fine. But what if we want to map what if we want to map one value to 10 other possible values? So one feature to 10 other possible labels, let's say. We'll keep it one feature for now, just so we're able to have, like a closer one-to-one mapping. But how am I describing this? Let's take a look at. Okay, so here in the training loop, we iterated over the data loader, or over, the data that's loaded by the data loader, and then we make a prediction. This is for batch and so in data loader. What does data loader have? I think it's here. Wait, what is this saying? Evaluating the model with no grad ensures that no gradients are computed during test mode. Okay. Okay, train data loader. That is up here. So if we are iterating over each, I forgot what the thing loads. So it loads like rows, right? It loads, or rather it loads data presented as rows. So you have the image and its associated label. Let me, okay, we can get rid of this. And this is just for loading the data. All right, data is loaded. So we have train data and test data. Okay, so let's do train data 0. It's not subscriptable. Did I do something different here? Oh, wait, I can do that with the data set, but with the data loader, there's a different way to go about it. What if I just print out train data? So I think I can iterate over this. So let's do I need to rush to prepare a class. I hope the NN goes well. Take care. Encoders, thank you very much for the raid and thanks for hanging out. I hope you have a good class and a great rest of your day. Thanks for the raid again. Okay, for I in train data, so we're gonna iterate over this thing. I believe that's how we had done it previously, right? Because we were doing next and iteration, and then we were calling next on the thing. Yeah, okay. So let's do this. Let's print out. Wait, that's gonna be a lot of statements. Oh God, stop, stop, stop. I forgot this train data has like 60,000 somethings in it, right? So don't want to be iterating over the whole thing. You know what? Wait. If what if I set the batch size to because I know that it's 60,000. What if I set the batch size to 60,000? What's the default if I don't set the batch size? The default batch size is 1. That's actually better. I didn't think about that. That is much better. It's still gonna iterate over the whole thing. Okay. Let's stop that. So let's do 60,000. Let's go back up and do 60,000. Or okay, no, you know what? We could do 15,000. So it iterates 4 times, and each sample contains 15,000, or each batch contains 15,000. Where is it? 15,000. Okay, so if I run this, actually, I should run type. So now it should run only 4 times. Okay, that returns a list, and then that's a list. Then that's a list, and then there's another list. All right. Um, it's returning a list. What if I wanted this as a tensor? Target transform doesn't do that, does it? Yeah, no, it doesn't. Target transform was for the labels. Does data loader have a transform option? Data loader combines a dataset and a sampler and provides an iterable over the given dataset. Okay. Let's yeah, let's just deal with it as it is. The thing is, I kind of wanted it as wait, okay, let's do a equals numpy array just so I can get like a shape or something. I mean, by that logic, I could also do a tensor, right? And then I can do tensor dot shape. Let's print a dot shape. So what I'm thinking is we have one row. Nope, there's a problem. What's the problem? Only one element tensors can be converted to Python scalars. It's a list. We are passing in a list. Okay, let's try numpy dot array. Nope, still setting an array element with a sequence. The requested array has an inhomogeneous shape after 2 dimensions. The detected shape was 2 and then 15,000. Okay. All right. Let's try. So it said 2 dimensions, right? So 0, 0, and then let's do 0. 15,000. So it says 2. 2 means 2 rows, and each row would be 15. No, wrong. It was supposed to be like this. Okay, let's print that out. Okay. Let's try that. So that's also 28, I guess. Yeah, so initially it was this 28. So this is 28, and then this is also 28, right? No, this has to be the row, because then this contains the columns. Meaning, the very last row or the very last dimension here is going to be one of the pixel values. No, nope, wait, no, that's wrong. Because based on what I'm seeing here, now if I access this, it's going to give me the row, the entire row, along with the column. So that's the row, and then the column. So wait, let's not iterate over this. Let's say train data equals next iter train data. Right, so we can get one iteration and then print that out. What if, hold on, what if I just wanted the first thing? Would that work, or do I still need to call? Yeah, no, I need to call next if I want it to be the next one. Okay. All right, so trying to reconstruct the dimensions of this, it looks like, so this is a row, because if I do this, it's zero, right? So, right, so this is a row. This is one row of 28 things, and there can be 28 such rows. Dude, what are the dimensions here? So, okay, this is a batch, right? Each batch, back up. We can try just looking at the training data set. Um, so in the training data set, we have this. So there's no batches here. Here it's just the images and their associated labels. Okay, so this is one entire row. And then we have all of the rows. So this is one image. This is one image. If I try to read the second thing of this, that gives me an error because it's out of bounds. Okay, what if I try to read the second thing of this? Int is okay. Oh, that's why. That's the label. That's the label. Okay. Okay, that's the label. And I think um I think this is of this shape because I remember we had to do the squeeze operation on it. I think it's of this shape. It's showing that it's a tensor, right? So if I read the shape of this, yeah, there it is. That's why we have to do the squeeze operation. Oh, dude, hold on. Give me a second. I just noticed the time. I just noticed the time. All right. Here's what we are gonna do. Okay. I am gonna go raid Little Witch Oz. Oz is cool people. She's currently doing uh she's she's animating her emotes, I think. Okay. I just looked at the time and I was like, dude, okay, it's time for me to, and besides my voice is also kind of giving out. So I'm gonna start the raid. Ian Encoders, once again, thank you very much for the raid. I appreciate you stopping by. I appreciate you bringing your people here. Um, what was the other person's name? Let me scroll up. Tej. Yes, Tej. Thank you for stopping by. And anyone else who might have been lurking in the chat, thanks for hanging out. I'm going to try and stream again tomorrow. I'm super excited, dude. There's so much for me to explore with neural networks now. And especially since today we have trained our very first neural network, I'm excited. I'm super happy with the results. And I'm going to keep exploring this. I might do my daily sculpting practice thing later on. I might do a mute stream later on for that. I'll see. But for now, I'm gonna carry on with this. I'm probably also gonna go and eat something because I haven't eaten anything since I woke up. But yeah, that's gonna be it for today's stream. I hope you guys have a nice day, and I'll see you all next time. Peace.